let's go back to this PowerPoint here. Now, this is exactly what I was saying. So I'm saying that, so suppose that we have, as an example here, this is some volume. So using calculus, suppose that I want to calculate the electric field at point P, then I can take my volume and break it up into small. And each of these units has a small volume and some amount of charge that I have in there, right? So each of these small volume has some amount of charge that is in there. And if I know the distance, for example, between this point and this point, then I can use this equation to calculate the electric field. But the point is that when the number of charges goes to infinity, then the summation is going to become an integral. And so this is the key equation that we have right there. So from now, everything that we're going to do is to use this equation to calculate the electric field. So when I use this equation here, all what I need to do is to set up, so just to set up the integral. When I set up my integral, I just need to know three quantities. How do I write my dq? Then what is my length? What is my distance vector r? And what is my unit vector r hat? So those are the three quantities that I need to know. I need to know dq, I need to know r squared, and I need to know the unit vector. So once you have those, you put it in that integral. Again, if this was something that I gave you in the exam, you have like a table of integral. So you just set up the integral and then you go to the table and look up the value, and then you can write down what the final result is. Now, as I said before, this dq here, the way we calculate dq is going to depend on, am I doing my calculation in a volume, in a surface, or I'm looking at a line, so this is volume. So if I'm doing calculation over a volume, this is how I write my dq. If I'm doing calculation over a surface, this is how I write my dq. If I'm doing it over a line, so dv, for example, is called the elemental volume. And so if you guys remember from your calculus, let me just share something here real quick. In calculus, suppose you have a function that looks like that, and then it tells you that this is point A, and this is point B. So this is the function f of x, and this is x. And we want to calculate this area here. So we want to calculate the area. So under the curve. Does anyone remember how to solve this problem? So if you have a function, and this function goes from point A to point B, and you want to calculate that area right there, how do you do that?
The integral from A to B of x.
That's correct. So to take the integral, now, do you see this dx right here? So the dx here, you can think about that as a length But what this really means is that to calculate this area, I need to take this area and break it up into smaller areas. So this is the x here, and then this is the x. So I'm just taking this and breaking this up into smaller areas. Now, the area of this small element here is just this small element here. You can think about this as the length, and this is the width here, so it's f of x. So this is the area of this small region right there. If I want to get the total, I just do the integral over all those contributions, right? So by taking an integral, what this means is that I'm just adding all the contributions that come from all the elements. So this is exactly what we're going to do to calculate the electric field. You calculate the electric field that comes from a small charge. Then using integral, you can get the contribution that comes from everything. So let's look at this one example. So let's look at this one example right here. So this is example number 23.1. Now, in this example, let's try to understand what the problem is talking about. So it gives us that the length is L, and this carries a total charge of Q. And I want to calculate the electric field at point P, where this is my point P right there. So, because this is just a line, when I calculate my dq, so I write my dq as that. Again, I'm just going back to this picture here. So if this is a line, I use this expression. If this is surface, I use that. If it's a volume, I use this. So because this is a line, I use this expression to get my E. Now, the distance from this dx to the point P, I can call that x. So it means that when you calculate this, you end up just getting this quantity here. And then to get the total contribution, you want to integrate from the point, let's say x equals to a to the point, x equals to b. Now, doing everything here, you get this quantity here. So if you do this integral and you simplify, you get this electric field. So notice that what we've done here, we just calculated the magnitude, right? But in terms of the unit vectors, this will be pointing in the negative I hat direction. Because remember, we always said that everything is a positive charge. So if this is a positive charge, when I calculate my electric field at point P, I expect the electric field to be pointing in that direction right there.